Hello everyone, this is Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering from Department of Electrical and Electronics Engineering, Hyderabad. So the course is about the power system operation and control. So we discussed so many components in this course, and this is about today's class, effect of tie line flow interconnected operation. So this parameter is usually interlinked to one of the load frequency control parameter, and if you introduce multiple areas as one of the tie line, so how the interconnected operation is going to begin. So that the points we will discuss in this case. So what is the effect of tie line flow in interconnected operations? So usually the flow of tie lines in an interconnected power system is going to affect the reliability, continuity and security operations of the power system network. When it comes to the case of reliability and continuity, so interconnecting power systems with the tie lines can increases the reliability and continuity of a new system. When it is under security constraints, this is interlinked to the economy as a security and economy constraint. So the feasible region of the tie line power transfer that can ready to improve the security and the economy of the interconnected power system networks. And it is also associated with one of the parameter called optimal utilization. So this is under the region of the tie line power transfer, which can ready to promote the optimal utilization of the generation dispatch. So the tie lines are transmission lines that are ready to connect the different areas from one boundary to another boundary. These are interconnecting networks. They make the system to be stable operating one at various boundary regions in the power system networks. So as of that, they allow the power system sharing of the loads in between those regions. So as a load frequency control is a daily operation that is ready to regulate the power flow in between the areas while it is ready to maintain a constant frequency. So load frequency control is ready to stabilize the system frequency. And also it makes the tie line power by controlling the area control error. We already discussed this parameter, area control error, that is of controlled output variables. So tie line bias control, that is TBC, is one of the method that will be commonly used in load frequency control operation for multi-area interconnected power system networks. So however, the applicability of tie line bias control to the load frequency can be complicated by the structure of the power system. So there will be some simple measures which will be considered as it is in the manner of TBC case. So this can be interlinked to LFC means. These unmanipulations may result into the operations of the power system network. So this configuration will increases the reliability and continuity of the new power system network. So that should be as a existing in nature. So in fact, reliability and continuity of service for two or more isolated microgrids also achieved by their interconnection through the tie line configurations. So usually in power system networks, the tie line is a transmission line. So that is connecting to the two or more electrical power systems, allowing for the transfer of electricity. Means one is connected here, another is connected one. Though this is represented with area 1, this is represented with area 2. So here it will be allowing the power transfer of the electricity in between them. The mutual sharing of the power in between these two boundaries are going to be takes place, which will derive from the other network. So here the lines play several crucial roles in the power system operation, and it will maintain that suitability of the operation as a separate case. So interconnection of the grids will be follows. They're ready to facilitate the interconnection of the different power grids or regions. So they may be enabling them to operate together as a larger network, and this network may influence the neighboring components, and this interconnection will helps to maintain the system reliability and stability conditions. So it is associated with the power exchange. So when power exchange is taken place in between the tie lines, they allow for the exchange of power between the different areas. We are having so many areas. There may be the lack of power in between the boundaries of the various power regions. So the exchange of power may going to be takes place in between these boundaries as it depends upon its nature of the power system network. So it may be towards their neighboring cases or one of the another and the remaining cases. So that exchange we may expect it, and that exchange usually beneficial during peak load conditions. That means when one area has excess generation, then the remaining another area is experiencing a shortfall. That shortfall is compensated by another neighboring boundaries. This may give one of the usual power balancing or power exchanging in between the lines. And one more parameter is frequency control that we already seen. So, but by connecting different power system networks, tie-line can help in balancing the generation and load. So, which is essential for maintaining the desired frequency in the interconnected power system operation. So, there will be economic benefits in maintaining load frequency control. So, they enable the trading of the electricity in between the regions and allowing them utilities to purchase power from other areas where it is cheaper to generate. So, like our state, Telangana, so they are supposed to be purchasing the power from Chhattisgarh. So, we are receiving the power from the Chhattisgarh. So, where it is even though long distance, will ready to receive the power to the one of the boundaries. So, here cost consideration is less compared to here. So here generation aspects are more in this state, and here we are receiving the power to make the continuity of the supply. So this can lead to low overall electricity cost for the consumers. If not, within the state or within the region, if you are generating the power and the same power is useful to the same load or consumers, means the cost of the power generation will may goes to increases. This will be more burden on the customers. So that's why to minimize these coefficients, we need to connect it with another areas. That boundaries may be larger or far away. Even though that, we need to expect the power from other boundaries. This may leads to reduce the cost of the power. Next case is integration of renewable energy. As more renewable energy sources are integrated into the grid, then tie lines can facilitate the transfer of power energy across the regions. They may helpful to balance the supply and demand. So we need to add more integrations just like renewable energy sources to one of the grid cases. So these can feed the power to the grid from various boundaries or from various regions, and the resultant may be the smooth conduction of the power operation. Smooth power conduction. So overall, the lines are essentials for the efficient operation, and the stability of modern power systems will follow, particularly in a case where electricity markets are increasingly interconnected in nature. Nowadays, all are interconnected in nature with the integration of renewable energy sources and some other power sources, due to which the load will be balanced and we can suppose it to meet the load requirement usually. So we can reach the demand usual case. And one more thing is reliability and redundancy parameter. So usually lines are provided redundantly and they are supposed to enhance the reliability of the power system. If one part of the system is experiencing a failure, then electricity can often be rerouted through the lines from other sources or other areas. So when there is a load sharing, in the event of the disturbance or outage in one area, the lines can help to share the load with neighboring systems. So because of this, preventing widespread of the blackouts may happen. This load sharing is done very smoothly. So now modern days power systems are divided into various areas. Like in India, there are 5 regional grids, like Eastern region, Western region. So each of these regions is generally interconnected for its neighboring areas. So the transmission lines that connecting the area to its neighboring area is called as the tie line. So that power sharing between two areas may happen through these tie lines. So for example here K is one of the area and J is another area. So the tie lines are existing in between K and J, where the area I is connected in between K and J, as the tie lines are connected on either sides of these two regions of K and J. So the existence of power flow in between the different areas is regulated by holding the frequency as constant. This we already discussed in the load frequency control. So all the power stations generators are kept in the synchronous condition with each other. That means which is a great task to achieve the perfect synchronizing condition. So in India we have operating frequency usually 50 Hz. So there will be a little bit variations like 0.5 Hz on a 50 Hz network. And in developed countries like UK and USA, we supposed to see the operating frequency ranges are 50 Hz. But Indian market, as per their power generations, we are expecting the frequency to be 50 Hz with some more little bit variations that will result in automatic load shedding or other control actions to restore the system frequency. So as a response of the feedback mechanism, they are going to operate at desired frequency ranges. Now with the change in system frequency, which may cause a change in its speed of the machines, that may ready to change the magnetizing effect there be for transformers and induction motors, which will be affected with the change in inductance. So there may be an expectancy of huge increase will causes the increase in harmonic currents and which will cause heating of the system. So with the insulation failure, these may also result so bad, and the frequency of the system also ready to decides the real power balance in the power system network, as the line parameters will changes with the changes in the frequency cases. So this regulation mechanism is supposed to be done by load frequency control, and here it comes with one of the tie line parameter which allows the bidirectional flow of the power. So here when we consider the curve with the frequency versus mechanical power P, then that variation is expected here. This is a delta P reference, change in reference, and that change may be expected with the delta F as one of the coefficient. That mechanical power is in terms of per unit, and also frequency also considered in per unit. That variation may drops as a delta reference. That may be existing in between the boundaries as a delta F from here to here, and from this point to this location it becomes delta PF. So as the system frequency increases, when the load is going to be decreases, then delta reference is kept at 0 value. Similarly, the frequency may decreases if the load is going to be increases. So however, it is desirable to maintain the frequency constant such that its delta F value becomes 0. Then the power flow through the different tie lines are supposed to be scheduled at various regions. Like area I may export a pre-specified amount of the power to the area J while importing to other, then pre-specified amount of power from the K area is going to be scheduled usually. So however, this is expected that to fulfill these obligations, but area I ready to absorb its own load change. So that maybe increases the generation to supply extra load in the area, or it may decreases the generation when load demand in the area has to be reduced. So while maintaining all these, the area must, however, maintain its obligation to the areas like J and K as far as importing and exporting power to the connected regions or connected boundaries. So this load frequency control has certain objectives to meet these load requirements that may ready to hold the frequency constant and the change in frequency as delta F0 against any load change. Then each area must contribute to absorb any load change such that frequency does not deviate. So each area must maintain the tie line power. So its pre-specified value. The first step in the load frequency control to form the area control error that we already defined as one of the tie line power, and that should be existing at synchronized power as tie line power and scheduled power case. So, and constant BF is called the frequency bias constant. With these suitable variables, we can suppose it to suggest for effective tie line power flow into the interconnected operations of the power system network. So that change in the reference of the power setting as delta P reference of the area I, it is then obtained by the feedback of the area controller. That should be through the integral control of the form. So where Ki is the integral gain and the area control error is negative, if the net power flow out of an area is low, then frequency has drooped characteristics. Then in this case, generation must be increased. This can be achieved by increasing delta P reference value to the extent of I case. So this negative sign accounts for the inverse relation in between delta P reference I and area control error. So that tie line power flow and the frequency of the each area are going to be controlled in the control center. Once the area control error is calculated as delta P reference, then I is obtained from the commands which are given to various turbine generator controls. This is ready to adjust their reference power settings to the required values. So here we will take a simple example. The tie line power is connected in between the two areas, area A and area B. Then these two areas A and B are interconnected through one of the line called tie line. So thus both the generation and load frequency are equal to a frequency range of about 50 Hz range. So there is no initial in this case, then the tie line power flow will going to be takes place. So these are supposed to be represented with one of the directional constants which are derived in between frequency versus power in megawatts. Then this line drawn as one of the L. So this is existing in between G to G dash, and these boundaries are expecting in between the frequency range starting with 49, 50, 51 Hz, as there is a little bit variation of 1 Hz, 2 Hz variations that may be expected as a delta L, delta TL, delta TL dash, delta TL W. As extension is happen in these lines, then the tie line powers are going to be very suitably. So some disturbances are occurs at B causing the frequency, which are dropped at a frequency level of 49.9 Hz. So area generation does not match with the effective load in the area A. The difference between I1 and I2, the difference existing in the generation and load may give us to net excess power in the area. So that flow out from the A towards B is going to be taken place. As this contributory effects in the area A decreases in the load power, then delta L and increase in generation delta G is going to be takes place. So that line flow from A to B as delta TL as one of the differential constant delta GA minus delta LA. So this is taken in terms of megawatt values. If the area A has AGC coefficient, then tie line flows are going to be increases as delta TL and delta TL dash, which is going to represent the increase in amounts of bias due to AGC coefficient. As the frequency change due to the disturbance delta B for a tie line power flow that is taken place from A to B, then delta F is delta B minus delta TL by 10 BB into B in Hz. As delta TL is taken place, then it becomes 10 BA into A, that may be delta AB by 10 BA into A plus 10 BB into B in megawatts. That net power change in B is delta AB minus delta TL as a 10 BB delta AB, which is equals to 10 BA into A plus 10 BB into B as product of this change in frequency delta. All these parameters are considered according to their regional boundaries, whichever we consider from this diagram. So, if that change is in terms of 10 BB delta AB, the additional value in terms of VA and BB is considered with the product of delta F. So, delta F by delta AB is considered as 1 by 10 BA into A plus 10 BB into B into B. So, this coefficient must be considered as one of the change in frequency constant. So, here is a simple example that may resembles as how the tie line coefficients are expected with the better pattern. For example, two areas A and B are interconnected. So, their generating capacity of the A is about to be 36,000 megawatts. This is with regulating characteristics of 1.5% by per 0.1 Hz. If B has 4,000 megawatts with 1% of 0.1 Hz, then here we need to calculate each area share of 400 megawatts. The disturbance with the increase in load occurs in the B region and which may result in the line flow, and the coefficient becomes delta F equals to delta AB by 10 into BA region multiplied with A plus 10 into BB region multiplied with B as 400 by minus 10 into 0.015 multiplied with 36,000 minus 10 into 0.01 into 4,000 coefficient. So, when you are substituting these numerals, then you are getting the negative sign frequency as minus 0.06896 Hz. So, then the line flow will be as a delta TL as a 10 BA into A into delta AB by 10 BA into A plus 10 BB into B. So, we already derived this condition from here. Then this becomes 5400 into 400 by 4800. So, this product will give one of the numeral that should be divided with 4800, which gives rise to 372.4 megawatts. So, smaller the systems, they need only 27.6 megawatts. That will be frequency regulations, maintaining much better case. As the parallel operation of the generators are taken place, that gives the maximum efficiency to the power system. That means continuity of the power supply is maintained in between the load and generator. This is generator 1, this is generator 2. When they are operating in parallel, then if any one of the generators fails to operate, then second generator will continue to feed the power to the load. This may happen usually. So, line flows and frequency droops are described for interconnected power areas, which are composite characteristics in nature. So, that is based on the parallel operation of the generator's case. So, each area must maintain its speed as 2F. Then a load common to both the areas are going to be treated. So, by superposition, it having the terminal voltage, that is V load equals to V1 sine omega 1t plus V2 sine omega 2t. So, here 1 and 2 represents areas 1 and area 2. T is the time factor which may be considered in seconds. So, generator speed versus load characteristics may be treated as one of the function of the type of the governor, which will be used on the prime movers of type 0 for a speed droop system and type 1 for constant speed of the system. As parallel operation of the generators with infinite bus is considered, then the characteristics will represent speed of the frequency per unit or load in per unit. These characteristics are considered as it will be ranges from 0.98 1.02 like that it will be follows, and load is about 0.51 like that it will be takes place. So here on either sides the two operations are existing. One is on the left side with motor operation, another one is with generator operation. These boundaries are taking one of the regions from highest peak value as delta P and delta F. Then constant system frequency will be maintained at infinite bus case. So this is to be achieved at a frequency range of 50 Hz usually. This will be happens as constant system frequency at infinite bus case. That's why we are saying about parallel operation of generators with infinite bus system. So generator characteristics are such that it is loaded up to 50% of its capacity when they are supposed to be parallel to the bus. Therefore, unit speed regulation may be achieved as one of the condition are, that will be delta F in per unit to the delta P in per unit value. So this delta F in hertz by 50 Hz gives to one of the denominator value delta P in megawatts by rated power in megawatts. So if it is desired to increase the load on the generator, then prime mover torque is supposed to be raises. So which will result in shifting of the speeding of droop curve that we already discussed here. This is the drooping of the curve. So which will result in shifting of the speed means the curve may ready to decrease, that the real power flow is represented by P equals to V1 V2 sin theta 1 minus sin theta 2 by X, where X is the coefficient of synchronous reactance. X is the coefficient of synchronous reactance. So these characteristics may multiply increases as one of the drooping nature, which may be speed or frequency in per unit to the load in a per unit case. That droop we may expected here like this. This is about to maintain a constant frequency for the infinite bus system. On the left hand side we are maintaining motor operation, and this boundary is existing with the generator operation. The drooping characteristics may be existing with the generator operation means it will be need to reach the values of constant frequency for the infinite bus system at about 50 Hz range. This gives to operate the smooth conduction of the power system network to produce the suitable amounts of power to the extent case. So which may rises to produce 100% suitability of the power system constraints. As we discussed already, as to reach this maximum conditions, one has to operate the two generators in parallel to each other. Even though any one of the generator malfunctions, then another second generator will tries to operate suitably. This may suitably achieved for this condition. So to achieve the respected values here, we need to maintain the system under parallel operating conditions under various load cases. So that may be operate in per unit system values. So per unit values are must consider to make the system over, to make the system under desired constraints. So which gives the suitability of the operations of the power system network. So as the motoring operation is considered means which may be ranging from 0 to 1. 1 means which are maintaining at 50 Hz constant frequency range. As we can compare with this range, what is happening means there will be delta P and delta F is going to be expected on either sides. But when comparing with this case, then load per unit may goes to hikes, as it is in the nature of the second case. As the load values are goes to high case, means we need to see that either the frequency range is coming with a constant or not. This we need to expect. So this can be supposed to be evaluated with the unit speed regulation coefficient as a delta F in H to the nominal frequency range about 50 Hz, and which will be maintained with the delta P by rated power under megawatts of range frequency. So this regulation we must choose according to the parallel operation of the generators within the infinite bus system. So this gives the better results when the consideration of effect of tie line power flow is interconnected in manner. So here the main benefit over this one means even any one of the system fails in the multiple connected areas, the second system or third or neighboring system may results to operate frequently. This may give good results as the system parameters are goes to heights. So this nature of the power system network may ready to make the smooth conduction of operations of the power system. So when you are introducing the constraints of these power system network under various frequency and load balancing cases, the power balancing can be achieved by maintaining all the suitable parameters to the constant range. If not that, then there may be difference in the power balancing condition, which may results to lapse of the power system network. So the regional boundaries are much more important in this case. When these regional boundaries are considered under suitable areas as area 1, area 2, area 3, area 4 means all the networks must suitably operate under same constant frequency ranges. So likewise, the effect of tie-line power flow for the interconnected power system network maintains the smooth conduction of the power system operation. So this makes the system to be stable. So these are some of the references which I have considered from electrical for you, and some video lectures and some engineering textbooks and PDF analysis and journal cases. That tie-line power constraints may give better results with these advanced networking technologies, which may suppose it to introduce for the power system. So this may goes to high for the smooth conduction of operations of the power system. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.